Okay, let's talk about Apache Hive. Essentially, it's a really helpful tool for working with data stored in Hadoop. Imagine you have massive amounts of information scattered across your computer. That's where Hadoop comes in. Hive acts like a translator, taking your everyday SQL queries, the ones you might use in a database, and turning them into instructions that Hadoop can understand and execute. It's fantastic for analysts who need to dig deep and find insights within this big data landscape. Let's talk about what makes Hive so powerful. At its core, Hive is all about making it easy to query massive amounts of data stored in Hadoop. A key thing to understand is that Hive uses schema on read. This means you define the structure of your data when you're asking questions about it, not when you initially store it, which gives you a ton of flexibility. It also provides a really familiar SQL interface, so if you know SQL, you can quickly start using Hive. Hive is fantastic for summarizing and aggregating huge amounts of information, and it's built to work seamlessly with Hadoop's parallel processing capabilities through MapReduce. Okay, let's talk about how Hive actually works. It's not just a simple SQL database, it has a really interesting architecture. At its heart is the metastore. This is where all the information about your tables lives, what columns they have, where the data is stored, and even some statistics to help speed things up. Then you have the Hive runtime, which takes those queries you write in HiveQL, which looks a lot like SQL, and actually runs them. It breaks down these queries into smaller pieces called MapReduce or test jobs, either of which are designed to handle massive amounts of data on Hadoop. The storage handler then manages where all that data physically sits, usually on HDFS. Finally, the resource manager makes sure each job gets enough computing power to do its work efficiently. Essentially, Hive acts as a translator, letting you use familiar SQL-like queries while still leveraging the power of Hadoop. Let's dive into the Hive metastore. It's basically a database that holds all the information about your data, and Hive think of it as the brain. It stores things like table schemas, which tell Hive what each column is and what type of data it holds. Plus, it keeps track of how your data is divided into partitions or buckets for faster querying. It's a really important component that lets Hive understand exactly where to find your data and how to work with it. Okay, let's talk about managed versus external tables in Hive. Think of a managed table as something that lives neatly inside Hive's organization. It's all tracked and controlled by Hive itself. It knows exactly where the data is stored, enforces the schema you define, and manages access for users. Now, an external table is different. It's like data sitting outside of Hive, maybe in HDFS or even on Amazon S3. While Hive knows about it, meaning it has metadata, it doesn't directly control how that data is accessed. You handle security and permissions through the storage system itself. Essentially, managed tables are for when you want Hive to be central to your data management, while external tables give you more freedom in where your data lives. Okay, let's talk about something really interesting in Hive schema on read. Think of it like this: with regular databases, you have to tell the database exactly how your data is organized before you load any information in. But in Hive, things are a bit looser. Schema on read means that you don't define the structure upfront. Instead, Hive figures out what the schema should be when you actually ask questions about the data. This offers huge flexibility, especially if your data is changing or coming from various sources with different formats. It also speeds up loading times because you don't need to spend a lot of time defining everything ahead of time. It's perfect for dealing with semi-structured things like JSON files. Okay, let's talk about creating tables in Hive. It's a really important first step. You need to define where your data will live. The create table command is how we do it. We specify the table name and then list out the columns with the data types, like integer, string, or whatever makes sense for your data. Then you tell Hive how to separate the fields within each row, usually a comma, but that can be customized. Finally, you decide how the table will actually store the data. Text file is a common starting point. Okay, let's talk about getting data into Hive tables, a really important step. There are several ways to do this, ranging from super easy to more complex. The simplest is probably load data local, which works great if your files are already on your machine. If your data's in HEFS, you can use load data in path. For updating or replacing whole tables, insert override is a good choice. And finally, when importing from databases like MySQL or Postgres, tools like scoop can be incredibly handy for bulk loading, basically getting the data in quickly and efficiently. Okay, let's talk about partitioning in Hive. It's crucial for performance. We have two main approaches, static and dynamic. Static partitioning means you define the columns that will divide your data asterisk when you create the table asterisk. Think of it like pre-sorting your files into folders before putting them all together. It's simpler to manage, especially if you know which filters you'll be using often. On the other hand, dynamic partitioning is more flexible. Hive figures out how to split your data based on asterisk how you're querying asterisk. It adapts as needed. This is great when you don't have a clear idea of what values will appear most frequently in your queries, or if those values change over time. Okay, let's talk about something really important for Hive performance: buckets. Think of them as like pre-sorted folders in your data storage. When you bucket a table by a specific column, say customer ID, Hive physically arranges the data on disk so that all records related to a single customer are grouped together in their own bucket. This is fantastic because it dramatically speeds up queries that filter or join based on those bucketed columns. Instead of scanning all sales records, Hive only reads the buckets relevant to the specific customer you're looking for, which reduces I/O and saves a ton of time. Let's talk about sorters in Hive. They're absolutely vital. Basically, a sort acts like a translator, converting the raw binary format Hadoop uses to store files into something Hive can understand, and back again when it needs to read your data. It handles serialization, which is writing Java objects into that binary format, and deserialization, which is taking those binary bytes and turning them back into usable Java objects for you to work with. Without sorters, Hive wouldn't be able to read or interpret the data stored in Hadoop. They ensure everything plays nicely together. Okay, let's talk about the types of files Hive can work with. It's pretty flexible. The most basic are CSV and TSV files, just comma or tab separated data. Then we have sequence files, which are great for storing Java objects efficiently. Avro is really useful when you need to send data between different programs because it has a good schema system. Finally, Parquet and ORC are columnar formats that are super optimized for running queries on big datasets. They're like the workhorses of analytics. Okay, let's talk about how Hive stores data. We have a few different file formats, each with its own strengths and weaknesses. Text files are the simplest, easy to read, but not very efficient for large datasets or complex queries. Sequence files are good for really big things, and they can change how the data is described as time goes on. RC files, record column files, are columnar, meaning the data is arranged by columns instead of rows. This makes them super fast when you're running analytics, pulling out specific pieces of information. Then we have ORC, which is another columnar format and often considered the best overall choice because it's highly optimized for Hive. And finally, Parquet. It's also a columnar format and gaining popularity due to its open source nature and excellent performance. Okay, let's talk about something super important when working with Hive: query execution plans. Think of them like a detailed blueprint for how Hive will run your SQL queries. They break down every step from reading the data all the way through to getting you the final result. You'll see things like table scans, how joins are performed, and even estimates on the cost of each operation. Understanding this plan is absolutely key because it allows you to spot potential bottlenecks and rewrite your queries for much faster performance. Basically, it's your guide to making Hive run smoothly. Okay, let's tackle a really important distinction: the difference between Hive and your typical RDBMS like MySQL or PostgreSQL. Think of it this way: traditional databases store data in rows and columns, just like a spreadsheet. They're fantastic for transactions where you need quick access to specific records. But when you're dealing with huge amounts of data, think terabytes or even petabytes, things start to slow down. Hive takes a different approach. Instead of storing everything neatly in tables, it stores the data as big text files on a cluster like Hadoop. It's like having a massive library where all the books are organized in a way that makes it super efficient to search for specific information, especially if you're looking at lots of columns at once. It uses SQL-like queries but relies on MapReduce or Spark under the hood to do the actual processing, making it perfect for big data analytics and business intelligence. Okay, let's talk about the differences between Hive and HBase. Think of Hive as a powerful tool for analyzing large datasets. It's like translating your SQL knowledge into a way to work with Hadoop. It defines its structure upfront, so you're working with well-defined tables. HBase, on the other hand, is more like a super-fast key-value store. It doesn't need as much pre-planning when writing data, and it's really great for applications that need immediate access to information, things like logging or real-time analytics. Both are vital in big data but excel at different tasks. Okay, so let's talk about Hive UDF. Basically, they're like adding your own mini programs to Hive. You can use them in SQL queries to do things that Hive doesn't already know how to do automatically. This is super useful if you need some complicated calculations or transformations, something beyond what Hive provides out of the box. They're also great for making complex queries easier to read and reuse your logic in multiple spots. Okay, so let's talk about UDAS and UDS and Hive. They are super powerful tools for extending what Hive can do natively. A UDAF is essentially a custom aggregate function. Imagine you need to calculate something very specific based on your data that isn't covered by the standard functions like count or sum. You write it yourself, usually in Java, Scala, or Python. It gives you full control over how those calculations are performed. Then there's UT, which stands for User-Defined Table Function. Think of it as a function that can pull data from external databases or systems and return a table back to Hive. They're really useful when you need to work with data that's not already within Hive itself. Okay, let's talk about Hive views. Basically, they're like virtual tables. They don't actually store data themselves. Instead, they hold a HiveQL query. It's like you've created a shortcut to a more complicated question in Hive. You can treat them just like regular tables when you're querying, which makes things much easier for users and allows you to reuse queries across different parts of your system. And importantly, views can also help with security. You could restrict access to the base data while providing a simplified view that only shows what's needed. Okay, let's talk about partitioning in Hive. It's a really important technique for handling big data efficiently. Imagine you have a huge sales table. Instead of storing all the sales records together, we can use something called partition columns to split the data into separate folders based on specific criteria like dates. This allows Hive to quickly narrow down the search when you're only interested in a particular time period, making queries much faster and saving a lot of resources. Let's talk about bucketing in Hive, a super useful optimization. Basically, it's like creating smaller groups within your data, or buckets, based on the values of a specific column, like product ID. Hive then uses a clever hashing process to automatically distribute rows into these buckets. This means that when you run queries, Hive doesn't have to scan all your data. It can just focus on the relevant buckets, making queries much faster and more efficient, especially helpful with large data sets. Okay, let's talk about partitioning and bucketing in Hive. They both help speed up queries, but they do it differently. Partitioning works by physically splitting your data into separate directories based on the values in a particular column, like data or region. This is great for when you frequently filter data based on those columns. Think of it as organizing your files neatly so it's easy to find what you need. Bucketing, on the other hand, groups rows with similar bucket ID within the same table. It's like having a special category for certain records. This is really useful when you're joining tables together because Hive can quickly locate matching data based on these common buckets. Basically, partitioning tells Hive where to store your data, while bucketing helps it find related rows efficiently. Okay, let's talk about vectorization in Hive. It's a really important concept for understanding how Hive queries run efficiently. Basically, instead of processing each row of your table individually, Hive can group multiple rows together into vectors. This means it can apply the same operation to all those rows at once. Think of it like doing several calculations simultaneously instead of one after another. This dramatically reduces overhead and allows for better use of the CPU, leading to much faster query execution times, especially when dealing with large datasets. Okay, let's talk about how we handle changes to our Hive tables. Schema evolution is really important when your data is constantly evolving, which it often is. There are a few ways to tackle this. You can use alter table to add or drop columns. That's the easiest for simple adjustments. If you need more significant changes, like completely restructuring a table, create table as select a CTAS as your friend, but be aware of potential data loss. Partitioning and bucketing can help too, especially when combined with CTAS to minimize performance issues. And finally, using Hive Schema Registry is fantastic for keeping track of all those schema versions across different environments, making it easier to manage everything. Let's talk about joins in Hive. Joining tables is fundamental for combining data and getting a broader picture of your information. Hive offers several different types, like inner, left outer, right outer, full outer, and even cross joins, although those last ones can be resource intensive if used incorrectly. Hive's clever map side join technique optimizes these operations by distributing them across the cluster. Understanding which type of join is most appropriate for your query will significantly impact performance. Okay, let's talk about how Hive joins tables specifically, map join versus sort merge join. Think of map join as a parallel processing approach where you're essentially assigning each key in one table to a different worker node for the join operation. It doesn't require pre-sorting beforehand, which can be great if your data isn't perfectly balanced. However, it can struggle when some keys appear much more frequently than others. This is called data skew, and it can really slow things down. On the other hand, sort merge join requires both tables to be sorted based on the join key before the join happens. Because of this pre-sorting, it tends to perform better with large datasets where the distribution of keys is relatively even, avoiding that data skew issue. So, map join offers more flexibility but can suffer from skew, while sort merge join excels when your data is sorted and balanced. Okay, let's talk about skew joins. They're really important when you're dealing with large datasets and joins in Hive. Imagine you have two tables, one is way bigger than the other. This creates a problem because Hive often tries to shuffle all those rows for one table into just a few reducers, which can slow things down dramatically. Skew joins are like giving each reducer a fair share of work by distributing the larger table's data across multiple reducers based on a key. Hive has a configuration option, Hive Skew Join, enabled that you can turn on to let it handle this automatically, often using partitioning based on an ID column as an example. Understanding skew joins helps you optimize your Hive queries for better performance. Okay, let's talk about how Hive sorts data. We have four main operators to consider: order by, sort by, cluster by, and distribute by. Order by and sort by are pretty similar. They both sort the entire dataset in memory, which is great for smaller files but can be a bottleneck with huge datasets. Cluster by is different. It partitions your data based on certain columns and then sorts with an asterisk each partition. This is really helpful if you often filter your queries using those same columns. Finally, distribute by distributes the data across multiple nodes and then sorts within each node. It's particularly useful when you're performing map joins to avoid shuffling massive amounts of data. Okay, let's talk about indexing in Hive. Think of it like an index in a book. It helps you quickly find the information you need without having to read every page. In Hive, we create these indexes on specific columns. They essentially sort the data for those columns, creating a sorted copy that Hive can use to speed up queries where you're filtering based on those index values. It's all about jumping directly to the relevant rows instead of scanning the whole table. Keep in mind that while this boosts query performance, it does require more storage space and slows down write operations a bit. Okay, let's talk about how to speed things up when Hive queries are dragging on. First, it's crucial to understand how Hive is running your query. Use the explain command to see the execution plan. This will highlight where it's struggling, like scanning entire tables instead of just specific parts. Then think about partitioning your data if you often filter by a particular column, and consider bucketing for columns used in joins or aggregations. Don't forget to keep Hive updated with statistics using Analyze table. Sometimes simply rewriting the query, like avoiding select asterisk, can make a big difference. And finally, experiment with different join strategies. Broadcast vs Mapstream to see which works best for your data. Okay, so let's talk about Hive Server. Basically, it's the main server that handles all your requests to run queries in Hive. It's like the central hub. It gets your questions in a language called HiveQL, figures out how to answer them efficiently, and then sends you back the results. It also keeps track of all the details about your data, like table names and what's stored where, thanks to the metastore. Okay, let's talk about Beeline. It's a really handy tool for working with Hive. Basically, it's like a super fast way to test out your SQL queries right from your IDE, things like IntelliJ or VS Code. Instead of running everything through the full Hive engine, which can take a while, Beeline uses Tez or Spark to execute those queries much more quickly. It's especially useful if you're just exploring data and want to get an idea of what's in your Hive tables without going through the lengthy process of submitting a full Hive job. It connects using JDBC, so it plays nicely with lots of different development environments. Okay, let's talk about how we interact with Hive. Traditionally, you'd use the Hive CLI the original way in, using Thrift directly over the Hadoop cluster. It's a bit slower though because of all the data translation happening behind the scenes. Beeline is a newer client designed specifically for Hive, and it uses a different protocol based on Impala, which is built on top of Thrift. That's what makes Beeline so much faster, often 2 to 5 times quicker than using the Hive CLI. It's also more efficient when it comes to resource usage. Okay, let's talk about the Hive compiler. It's honestly one of the most important parts of how Hive works. Think of it as your data's translator. When you write a query in HiveQL, which looks very similar to standard SQL, it doesn't directly tell Hadoop what to do. The compiler takes that high-level query and breaks it down into smaller steps. First, it checks if the query is valid, like making sure you have the right table names and column types. Then, it tries to simplify things as much as possible using logical optimizations. This can involve rearranging how your data is processed. Finally, based on these simplifications, it creates a plan for Hadoop, whether that's MapReduce or something else, telling it exactly what steps to take to get you the results you need. Okay, let's talk about the warehouse directory. It's a really important part of how Hive works. Think of it as Hive's dedicated home base on HDFS, where all the data from your queries get stored. It doesn't just run SQL directly against the raw files. Instead, it translates those queries into jobs that process and store the results in this directory. The default location is usually under /user//, but you can actually change this to control where your data lives, which is super handy if you're working with multiple users or need to organize things differently. Okay, let's talk about how Hive tackles complex data types, specifically arrays and maps. Think of arrays as ordered lists of things, like a shopping list with items in a specific order. You define them using square brackets inside your Hive table definition. You can insert array elements directly into the table using the syntax. And to work with those individual items, you've got functions like size and array contains. Now, maps are essentially key-value pairs, like a dictionary where you look up information based on a name or key. They use curly braces to define them. You insert map data using the syntax and access values by their corresponding keys. These features make Hive really powerful when dealing with data that doesn't fit neatly into rows and columns, offering flexibility for working with various data formats. Okay, let's talk about how Hive actually runs your queries. There are a few different modes it can use, and understanding these is really important for any Hive interview. The oldest way was called MapReduce mode. Think of it like sending your SQL instructions to a giant computer that breaks them down into lots of smaller tasks and then puts them back together. While it worked, it wasn't the fastest. Then came Tez, which is basically an in-memory step between Hive and MapReduce, making things much more efficient by caching data and reducing unnecessary shuffling. Spark mode does a similar thing but uses Spark's powerful distributed computing capabilities for even faster processing. And finally, there's direct mode, where Hive server runs the queries directly. This is great for smaller, quick jobs. Okay, let's talk about how Hive actually runs your queries. There are really two main ways it can do this: local mode and distributed mode. Local mode is pretty straightforward. Everything happens on one machine, like the one you are using to run the Hive command line. It's quick and easy for small datasets, but it quickly hits a wall when dealing with anything larger or more complex. On the flip side, distributed mode utilizes the power of a Hadoop cluster. That means your query gets broken up and processed across multiple machines simultaneously. This is fantastic for really big data. However, setting it up is a bit more involved, and you need to make sure your Hadoop cluster is running smoothly. The key takeaway is that local mode is all about one machine doing everything, while distributed mode spreads the work around. Okay, let's talk about Hive and how it works with Tez and Spark. First up is Hive on Tez. Think of Tez as a super smart scheduler for your MapReduce jobs. It really helps to speed things up when you're running complex queries that are already written in the traditional MapReduce style, those kinds of big data transformations and aggregations. Then we have Hive on Spark. Spark is like a lightning bolt. It processes data much faster, especially if it can keep things in memory. This makes Hive on Spark great for things like machine learning or when you need really quick answers from your queries. Okay, let's talk about ORC-optimized row columnar. Think of it as a super efficient way to store data in Hive. Instead of storing rows one after another like a spreadsheet like CSV, ORC stores the data by columns. This means when you're running a query that only needs a few specific columns, Hive doesn't have to read the entire row, just those columns. It also compresses the data really well, saving space and time. Plus, if your data schema changes, let's say you add a new column, ORC makes it easy without needing to rewrite everything. It's a big win for performance and flexibility in Hive. Okay, let's talk about how Hive keeps track of everything. At the core of it all is something called the metastore. Think of it like a central database that holds all the information about your Hive tables, exactly what's in them, where the data files are stored, and even how big they are. When you create a table, the metastore registers its definition, making sure everything's properly documented. Then, as you run queries, Hive uses this metadata to understand the structure of your data and figure out the best way to process it, optimizing performance along the way. It's really clever how it tracks where all the data lives, so you don't have to do that manually. Okay, let's talk about certs in Hive. Basically, they're the bridge between how Hive stores data and how *Q* access it. Hive uses its own optimized format, often ORC or Parquet, but your applications usually work with things like JSON or CSV. The cert takes care of translating that back and forth. It serializes data when you write to Hive, turning your application's format into Hive's internal one, and it serializes the data when you read from Hive, converting it back. They also manage the schema, making sure everything is compatible. So, certs are super important for getting your data in and out of Hive smoothly. Okay, let's dive into how we manage data changes in Hive. When it comes to deleting rows, the delete statement is your go-to tool. Think of it like SQL delete. But remember, Hive doesn't have a direct truncate table, so you'll need to use the where clause to be precise about which data gets removed. And if you are working with partition tables, deleting specific partitions can really speed things up. Now for updates, we use the update statement just like you'd expect. Again, using that where clause is key to only modifying the rows you intend to change. Keep in mind that updates can take longer than inserts because Hive has to process everything across its distributed environment. And if you're dealing with critical data, investigate Hive's transactional capabilities. They can offer more reliability for your updates. Okay, let's talk about ACID transactions in Hive. Essentially, they're like making sure your data stays consistent and reliable, just like you'd expect from a regular database. ACID stands for atomicity, consistency, isolation, and durability. Atomicity means that all changes within a transaction either happen completely or none at all. Consistency ensures rules about your data are always followed. Isolation makes sure concurrent operations don't mess each other up, and durability guarantees that once something is saved, it stays saved even if the system crashes. Hive uses something called Hive to provide this transactional support, leveraging a technique called MVCC to manage changes efficiently. Okay, let's talk about how Hive handles inserting data into your tables. We have two primary ways to do this: overwrite and append. Think of overwrite as a complete reset. It completely deletes the existing table and rebuilds it with all the new information you're providing. It's great when you want to start fresh. On the other hand, append is more like adding to something. It takes your new data and just adds this rows on to the end of an existing table without touching anything that's already there. So, if you're updating a table with small amounts of new information regularly, append is often what you'll want to use. Okay, let's talk about multi-insert queries in Hive. Basically, when you're loading a huge asterisk amount of data into a table, the standard insert statement where you add each row individually can be really slow. A multi-insert query changes that. Instead of adding rows one at a time, Hive bundles them all together and processes them in bulk. Think of it like loading a truckload versus delivering individual packages. This drastically improves performance, reduces the load on your system, and makes it much more scalable for dealing with large datasets. Okay, let's talk about load and insert in Hive. They're both used to get data into your tables, but they do different things. Load essentially pulls data directly from a file like a CSV or text file and dumps it straight into the table. It's great for bringing in external data, but it can be slower for huge files because Hive has to read each row individually. On the other hand, insert takes data from an existing Hive table and copies it over to another table. It uses the schema of the source table, so it's generally much faster when you're moving data around within Hive itself. So, remember, load for outside files, insert for within Hive. Okay, let's talk about staging tables in Hive. Basically, they are like temporary holding areas for your data as you work with it. When you have a really big dataset and you're doing some complex transformations, cleaning, joining, filtering instead of loading everything directly into the final table, Hive often loads it first into a staging table. This helps speed things up because Hive can process smaller pieces of data at a time. Also, if something goes wrong in one step, you don't have to restart from scratch. You can just roll back to the staging table. It's a really important technique for making your Hive queries more efficient and less prone to errors. Okay, let's talk about writing custom CRDs in Hive. These are essential when you're dealing with data formats that Hive doesn't automatically understand, like JSON or Avro, for example. They allow you to handle different schema changes and even optimize the process for specific needs. You'll essentially create a Java class extending the base CRD class, then override key methods like transform row and save record. Finally, you register your custom CRD with Hive so it knows how to work with those formats. Think of it as providing Hive with the instructions on exactly how to read and write your data. Okay, so let's dive into Hive's built-in functions. These are your go-to tools for working with data, making it easier to clean, transform, and analyze information. We've broken them down into categories: string functions like concatenating and trimming text, numeric functions for rounding numbers, and even date and time functions for formatting dates. Knowing these is essential for any Hive interview. Okay, let's talk about something really useful in Hive: windowing functions. Basically, they allow you to do calculations across groups of rows instead of just looking at individual records. Imagine calculating the average order value for all customers within a month. That's what windowing helps with. You define these windows using the over clause, specifying how your data is partitioned and ordered. Then you apply functions like avg, sum, or mi into those groups. It's like applying calculations across a team of people instead of just one individual. And as you can see in this example, it's incredibly helpful for things like calculating cumulative values over time. Okay, let's talk about the explain command in Hive. Think of it as a peek behind the curtain to see how Hive plans to run your query. It doesn't actually execute the query, but it gives you a detailed execution plan showing exactly how Hive will break down your instructions, which tables it needs to pull data from, and the order in which everything gets done. It even tells you about potential costs involved. By looking at this plan, you can spot any areas that might be slow and adjust your queries to improve performance. Okay, let's talk about the default storage backend for the Hive Metastore. By default, it lives on your local file system. Think of it like a really organized folder on the same machine running the Metastore. It's simple to set up initially, especially when you are developing or working with smaller data sets. However, as things grow bigger and more users start accessing it, that local file system can become a major bottleneck. Think about it, lots of people trying to read from and write to the same folder at the same time. So while convenient for getting started, remember that scaling up often requires switching to something like HDFS or cloud storage solutions for better performance and reliability. Let's address a really important question about Hive. What happens when the Metastore, that crucial database holding all our table information, goes offline? The short answer is things grind to a halt immediately. All your queries will fail, you won't be able to read or write data, and any running jobs just stop. Think of it like trying to drive a car without an engine. Fortunately, there are steps we can take to recover quickly. Restarting the service is often the easiest fix. If that doesn't work, restoring from a backup is ideal. And as a last resort, we can manually recreate the schemas, but that needs careful planning. Okay, let's talk about how Hive keeps your data safe. First off, there are a few different ways we can authenticate, essentially verify who someone is. We've got Kerberos for the strongest security, username/password, which is good for getting started, and LDAP if you already have an existing directory set up. Then, once someone's in, authorization controls what they can see and do. Think of ACL as very specific permission lists at the table or even individual columns level, and RBAC lets you assign users to roles with predefined access rights. Finally, we have encryption, both protecting your data when it's stored encryption at rest and during transit using SSL/TLS. It's a layered approach to make sure everything is secure. Okay, let's talk about how Hive can connect to other databases. Often, you'll have data already sitting in systems like PostgreSQL or MySQL, and you want Hive to work with it. The key is that Hive's Metastore, where it stores information about your tables, can be told to look at those external databases as the source of truth for all that table information. You essentially give Hive the address of the database using a JDBC URL, along with credentials like a username and password. It's important to make sure you have the right JDBC driver installed in Hive, and that the user running Hive has permissions to access the data within the external database. Finally, you'll need to configure Hive's Hive site XML file with these connection details, properties like how to connect to the database and authenticate. Let's talk about how Hive handles changing its data structure. Schema evolution is all about making adjustments to your database design as your needs evolve, and it used to be a major headache for Hive. Traditionally, if you wanted to add a new column or change the type of an existing one, you'd often have to completely rewrite the entire table, a slow and disruptive process. But with formats like ORC and Parquet, things are much smoother. These formats store metadata alongside the data itself, making it incredibly efficient to update the schema. Instead of rewriting everything, only the metadata files get touched, keeping read performance high even as your schema changes. It's a big win for flexibility and efficiency in Hive. Okay, let's talk about Hive and Impala. Both are tools for working with big data in Hadoop, but they have really different strengths. Hive is like a traditional data warehouse. You set up your queries and it processes them later, often overnight. It's great for reports and moving data around ETL. Impala, on the other hand, is designed for speed. It's a real-time query engine, so when you ask it a question, it answers almost instantly. Think of it like asking a friend a quick question instead of waiting for them to write down an essay. Impala excels at interactive analytics and building dashboards that need fast responses. Okay, let's talk about Hive versus Spark SQL. They're both awesome tools for working with data, but they have distinct strengths. Think of Hive as a really efficient way to process huge amounts of information in batches, like moving mountains of data from one place to another. It uses something called MapReduce, which is a bit older technology. Spark SQL, on the other hand, is much more nimble because it runs primarily asterisk and asterisk your computer's memory rather than relying on those giant batch processes. This makes it incredibly fast for interactive queries and things like data science projects or even real-time analytics. You can think of Spark SQL as a go-to choice when you want to quickly explore and analyze your data. Essentially, Hive is great for big batches, while Spark SQL is fantastic for speed and flexibility. Okay, let's talk about lateral views in Hive. They are super handy when you need to pull information from different tables that aren't directly related to a common key. It's like having a magical window into multiple datasets at once. You define the view using the lateral view clause, and then you can query it just like any other table. This simplifies your queries significantly compared to traditional joins, especially if your data is spread out across several tables. They can sometimes even be more efficient than joining those tables directly, but it's always good to test and compare. Lateral views give you a lot of flexibility in how you model your data relationships. Okay, let's talk about how Hive deals with JSON and XML. It doesn't magically understand them straight away. The key is SERDA, that's short for serializer/deserializer. Think of it as a translator. You need to tell Hive * which * translator to use for your specific format. For JSON, you'd typically use the JSON SERD, and for XML, you'd leverage the XML SERD. But here's the really important part. You absolutely have to define a schema for your table that matches how your data is actually structured within the JSON or XML file. Hive uses this schema to figure out what each value represents, whether it's a string, a number, or something else. A mismatch between your schema and your data will cause problems, so pay close attention to those details. Okay, so let's talk about Hive external tables. Think of them as a way for Hive to peek at data that's already living elsewhere, like in a big data lake or even an older system. It's not actually moving the data into Hive, it's just creating a descriptional little map telling Hive where to find it and how it's structured. This is super handy when you're working with data in formats that Hive doesn't automatically understand, or when you need to pull information from a system that isn't directly connected to Hive. Okay, let's talk about variable substitution in Hive. It's a really powerful technique for making your queries more adaptable. Basically, it lets you build SQL statements on the fly using values that aren't hard-coded into the query itself. We have a few key ways to do this. First, there's string concatenation, which uses the operator to stick strings together like hello and world. Then we've got string replacement with the replace function, perfect for swapping out parts of a string. Next up are conditional expressions using case statements. You can build different SQL logic based on whether a value is greater than 10 or not. And finally, you can use subqueries in dynamic SQL to create very complex queries, building the whole statement piece by piece using string concatenation. But remember, always sanitize your variables to be safe from potential problems. Okay, let's talk about getting data out of Hive. There are several ways to do this, and it really depends on where you're sending the information. A popular tool is scoop. Think of it as a bridge between Hive and your relational databases like MySQL or Postgres. Then there's Hive itself, allowing you to run queries directly to pull out specific data. And for larger datasets, exporting in an ORC format can be super efficient when loading into other systems that support columnar storage. It's important to think about the size of your data and what your destination system needs. Is it a big batch job, or do you need quick access? Don't hesitate if you have any questions. Okay, let's talk about the differences between Hive and Pig. Both are powerful tools for working with big data on Hadoop, but they have very different approaches. Pig uses a language called Pig Latin. You tell it what you want to do with your data, almost like describing a recipe. Hive, on the other hand, is more SQL-like. You specify how you want things done, and Hive translates that into MapReduce jobs, which are then executed by Hadoop. So Pig focuses on describing the process, while Hive focuses on the execution. They're both great for big data, but suited to different needs. Hive is generally better for complex queries and warehousing, while Pig excels at quick prototyping and simpler transformations. Okay, let's talk about when Hive really comes into its own. It's often used as a way to make big data accessible through SQL. Think of it like building a BI layer on top of Hadoop. You can run standard reports and analyses against massive datasets stored in HDFS. It's fantastic for analyzing logs, like those from web servers or applications, and even processing clickstream data to understand how users are interacting with websites or apps. You might also use Hive within an ETL process to transform and load data into a more structured warehouse. Finally, it's great for quickly exploring data when you just need to poke around and see what's there. No need to write complicated MapReduce jobs every time. Okay, let's talk about materialized views in Hive. Basically, a materialized view is like creating a backup of the result of a query. It's a stored snapshot of the data. When you run a really complex or time-consuming query, Hive will execute it once and then store the outcome in a new table called a materialized view. So, if you need to run that same query repeatedly, instead of having Hive recalculate everything each time, it just pulls the pre-computed results from the materialized view, leading to much faster performance and lower costs. Okay, let's talk about how Hive deals with null values. By default, an empty string in a column is treated as null. When you're doing calculations or comparisons, if either side of the equation is null, the whole result will often be null too. To avoid this, you can use functions like coalesce and ifnull. Coalesce lets you provide multiple fallback options. It returns the first non-null value. Ifnull is simpler, taking just two arguments, the expression to check and a default value to return if it's null. Both are super useful for making your Hive queries more robust when dealing with missing data. Okay, let's talk about a really important optimization in Hive called vectorized query execution. Traditionally, when Hive processes large datasets using MapReduce, it handles each row independently, like processing a long line of code one step at a time. This can lead to a lot of shuffling and merging as data needs to be moved around between different nodes. Vectorized execution flips that approach. Instead of treating each row as separate, Hive groups multiple rows together into vectors. It then performs an operation on the entire asterisk vector at once. Think of it like running a single command across a whole set of instructions. This dramatically cuts down on the amount of data shuffling needed, which makes processing much faster and allows for better use of your cluster's resources. It's particularly beneficial for things like joins and aggregations where you're dealing with lots of related rows at the same time. Okay, let's talk about compression in Hive tables. It's a really important part of working with big data efficiently. Basically, Hive can compress the data stored in its tables to take up less space on your storage system, which saves you money and time. There are several ways it does this. The most common is Snappy, which is fast and offers a good balance between speed and how much smaller the data gets. Then there's gzip, which compresses more tightly but takes longer. LZO is another option that's very speedy, and bzip gives you the best compression rate, but it's also the slowest. You can control all of this using Hive configuration properties. It's a trade-off. Think about how much space you need to save versus how quickly your queries run. Okay, let's talk about compression in Hive. When you're storing data, using a compression code can really help save space and speed up queries. Hive has a few options available. The default is Snappy. It's super fast for both compressing and decompressing the data. Then there's gzip, which gives you better compression but takes a little longer to work with. LZO used to be popular for its really tight squeeze, but it's less common these days due to licensing issues. And finally, bzip offers even more compression than gzip but can be slower still. You can tell Hive which codec to use when you create or alter a table. There are commands in the Hive CLI that let you set the default. Okay, let's talk about configuring Hive's execution engine. It's a really important step in optimizing your queries. Basically, this part of Hive is responsible for actually running your SQL statements. The most common options are TZ and MapReduce, but you can also use MR2. The Hive execution engine setting tells Hive which one to use. TZ is generally the best choice. Then there are settings like the MapReduce class and key name. These control how jobs get scheduled and where they run. Finally, the execution mode decides whether your queries will run locally or on a distributed cluster. It's all about finding the right balance between performance and resource usage, so don't be afraid to experiment. Okay, let's talk about how Hive handles configuration. You've probably heard of SCT and HiveConf, and they seem similar, but there are some important distinctions. Think of SCT as temporary settings, like adjusting your personal preferences for a specific session in Hive. You can change them at any time during that session. It's a quick way to tweak things just for you. On the other hand, HiveConf is more about setting defaults for the entire Hive process. It's a broader command that affects how the metastore, executors, and other components behave. Essentially, SCT controls your individual session, while HiveConf influences the overall execution environment. Okay, so let's talk about how Hive and Yarn work together. Imagine you write a SQL query in Hive. First, Hive checks its metastore for the table details. Then it breaks down that query into smaller pieces. These are often MapReduce jobs, or if you're using Hive on Spark, they might be Spark jobs. Hive then hands those optimized instructions over to Yarn, which is like the traffic controller of your Hadoop cluster. Yarn figures out where to put them, what machines need resources, and allocates containers for them to run. The actual processing happens inside those containers, and finally, the results are stored back in HDFS, all thanks to the Hive metastore keeping track of everything. Okay, so let's talk about multi-table inserts in Hive. Basically, it's a really clever way to load data into multiple tables at once, all within one statement. Instead of running separate insert commands for each table, which can be super slow with large amounts of data, Hive's optimizer figures out the best way to write everything efficiently. Think of it like a streamlined process that reduces trips back and forth across your network. The syntax is pretty straightforward. You use a comma-separated list of tables in the insert into clause followed by a select statement from your source table. It's much faster, simpler, and more efficient than doing things piece by piece. Just remember that all those tables need to be compatible in terms of this scheme. They have to line up properly for this to work seamlessly. Okay, let's talk about speculative execution in Hive. It's a clever trick to boost performance. Basically, Hive looks at your query and tries to figure out which paths might take the longest. Then, it makes educated guesses and starts working on those stages ahead of schedule, like prepping some ingredients before you even know how the whole recipe will turn out. This can be really helpful if your predictions are correct, speeding up the entire process considerably. However, there's a catch. If Hive is wrong about which parts are slow, it could lead to inaccurate results, so it's all about smart guesses and careful optimization. Okay, let's talk about recovering from failed queries in Hive. It happens. The very first thing you want to do is check the logs. They're your best friend here. You'll find all sorts of clues there. Then, use Hive query history to see if a previous query might have caused problems. Sometimes just trying again will work. Other times it's about tweaking configurations like parallelism or memory. If you're seeing corrupted data files, which can happen, deleting and recreating them can help. Finally, be careful with the hivef command. Use it for investigation, not as a quick fix. Always dig into why it failed in the first place. Okay, let's talk about Hive indexes. Basically, they're like indices in a book. They help Hive quickly find specific rows when you run a query. Historically, they were almost mandatory for good performance, especially with older versions of Hive and the MapReduce engine. But things have changed. With the newer TES execution engine, Hive's optimizer is much smarter about how it plans queries, often avoiding the need to scan entire tables completely. So, while they still can be helpful, particularly on gigantic tables or when you have very specific query patterns, they're not as critical as they used to be, and you really need to consider the extra storage space they take up. Okay, let's talk about scheduling those Hive queries. First up is Uzi. It's a really established workflow scheduler for Hadoop environments. You basically create workflows using XML files that clearly lay out the steps and what needs to happen before each step can run. It's great for complex pipelines. Then we have Airflow, which is a more modern option. Instead of XML, you use Python code to define your workflows as DAG. Those are directed acyclic graphs, which visually show the dependencies between tasks. Airflow also has a fantastic web interface that makes it easy to monitor everything and see what's going on. Ultimately, the best choice depends on your setup, so think about the complexity of your pipeline and how important ease of use is for you. Okay, let's talk about the Hive warehouse connector and its role in Spark. Think of it this way: for a long time, Hive was the place to store your data if you needed batch processing like running reports or doing nightly updates. But Spark was amazing for interactive queries and quick analysis. The problem? They didn't always play nicely together. The HWC is what solves that. It's basically a translator, letting Spark directly read from and write to Hive tables without needing to convert the data first. This cuts down on moving data around, saves storage space, and ultimately makes your analytics much faster and more efficient. It's really about bringing the best of both worlds together. Okay, let's talk about migrating those Hive workloads over to Spark SQL. It's a really smart move for many organizations looking to boost performance and scalability. First, you need to really understand what your Hive queries are doing, where the bottlenecks are, if there's any data skew causing problems, and just generally how complex they are. Then consider things like data formats. Parquet and ORC are often excellent choices for Spark because they're compact and fast to read. Spark has a fantastic query optimizer that can help you rewrite queries for better results too. Finally, plan for schema changes. Make sure everything lines up smoothly between Hive and Spark. The migration process itself involves rewriting your queries, transforming data using Spark's powerful data frame API, replicating partitioning strategies, and most importantly, rigorous testing to ensure the new Spark queries are giving you the same accurate results as your original Hive ones. Okay, let's talk about a really important difference in Hive ACID tables versus non-ACID tables. Think of it like this: ACID stands for atomicity, consistency, isolation, and durability. Those are core database principles. When you create an ACID table in Hive, it's built to handle transactions, ensuring that if something goes wrong during an update or insertion, the whole thing rolls back cleanly. It's great for things like financial records, where you absolutely need data integrity. On the other hand, non-ACID tables are simpler and faster. They are designed for speed, especially when dealing with massive amounts of data. They don't have the strong consistency guarantees, so it's more suitable for tasks like analyzing logs or building a large data warehouse where immediate precision isn't as important as getting the job done quickly. Okay, let's talk about ACID properties in Hive and how they apply to tables. Full ACID tables are a big deal. They guarantee that all your data changes happen reliably as a single unit of work, maintaining consistency and preventing conflicts between transactions. They use something called HiveX, often backed by Derby or SQLite, to achieve this. Now, insert-only ACID tables take things a step further for specific scenarios where you're only adding new data. They still provide atomicity, consistency, isolation, and durability, but with a critical limitation: you can't update or delete any existing rows. This is perfect if you know all your data will be added, but it really restricts what you can do with the table. Okay, so let's dive into something really important when dealing with Hive ACID tables: bucketing and versioning. Think of buckets as smart dividers within your table. They help speed up queries by splitting the data into smaller pieces. Now, when multiple users are updating this table at the same time, it can get tricky. Hive uses a clever versioning system to make sure everyone's changes are consistent. It's like creating a history of each bucket, so if something goes wrong, Hive can rewind and fix it. This ensures that no data is lost and everything stays in sync. It also makes rolling back updates super easy, which is really helpful for debugging or correcting errors. Okay, let's talk about analyzing your Hive tables. It's a really important step. Before diving into complex queries, you want to get a good understanding of what the data ** actually * looks like. There are several easy ways to do this. First, describe table name will give you all the details about the table, its schema, data types, basically everything you need to know. Then, sampling with select asterisk from table name limit 10 can give you a quick peek at the first few rows and help catch any formatting or data type issues early on. Finally, show create table will show you exactly how the table was built, including any partitions it might have. And don't forget to use HiveQL queries like count, sum, average, etc. to quickly see the range of values within your columns. So when do you actually need to analyze a table? Well, anytime you're unsure about its structure, if you suspect data quality problems, or if you want to optimize query performance, it's always good to take a quick look. Okay, let's talk about compaction in Hive's ACID tables. These tables are designed to be reliable and consistent, but a key thing to understand is that as you continuously update or insert data, the table can become fragmented, meaning it ends up with lots of small files stored within its directory. Compaction is like tidying your desk. It's the process of merging these smaller files into fewer, larger ones. This reduces the number of files Hive has to search through during a query, leading to much faster performance. It's especially important for ACID tables because maintaining consistent metadata, which is what ensures those reliability properties, relies on a well-organized file structure. So, regular compaction is really key to keeping your ACID tables running smoothly. Okay, let's talk about auto-compaction in Hive. It's like a super smart file organizer for your data. Basically, when Hive finds lots of really small files that contain similar information, it automatically combines them into fewer, bigger files. This makes queries run much faster because Hive doesn't have to scan as many individual files. Think of it like searching one giant folder instead of dozens of tiny ones. It also saves space on your storage because you're consolidating all that data. However, keep in mind that doing this can sometimes slow down the process of writing data into Hive, so monitoring is important to find the right balance for your workloads. Okay, let's talk about tackling those pesky Hive query failures. The very first thing you need to do is dig into the logs. They're your best friend here. Look for any error messages or stack traces that give you a clue as to what went wrong. Then, double-check your data. Sometimes problems start with incorrect or mismatched information. Finally, keep in mind common culprits like syntax errors, type mismatches, partition issues, and even resource limitations. Hive can be sensitive to these things. Okay, let's talk about resource plans in Hive Lab. Think of it like a detailed roadmap for your queries. It tells Hive exactly how to break down the work and use the available resources on your cluster. It's all about intelligently assigning tasks to different nodes so you get the best possible performance. The plan looks at things like how many worker nodes you have, how much memory they each have, and then figures out the most efficient way to move data around, particularly during shuffle stages, which can really slow things down if not done right. It's a dynamic process, adjusting based on query complexity and the size of your data. Okay, let's talk about Hive Lab. It's a game changer for anyone working with Hive. Basically, Lab is like giving Hive super speed. Instead of just processing data step by step like old Hive used to do, it looks ahead at the whole query first. This allows it to figure out the best way to get those results quickly, often skipping a lot of extra steps and shuffling around data. That means you'll see much faster interactive queries, less waiting time, and an overall smoother experience when exploring your data. It's especially useful if you're dealing with really big datasets or complex questions. Let's talk about column pruning in Hive. It's a really important concept for optimizing your queries. Basically, when you run a Hive query, the engine figures out exactly which columns are actually needed in the final results. Then, instead of reading the entire dataset and extracting all those columns, it only reads the partitions that contain those specific columns. Think of it like this: you're only bringing in the stuff you need, not everything. This dramatically cuts down on data transfer, speeds up query execution, and even saves storage space, making your Hive queries much more efficient. Okay, let's talk about getting Hive data into your BI tools. It's a really common question in interviews. There are several ways to do this, and the best approach depends on what you're using. The simplest is often direct querying, where tools like Tableau or Power BI can connect directly to your Hive tables, pulling data right in. You can also use Apache Atlas to help with metadata discovery. It's great for knowing exactly what you have available. JDBC connectivity offers a more flexible option, and if you're using formats like Delta Lake or Iceberg within Hive, that opens up really smooth integration with modern data lakehouse BI tools. Okay, let's talk about authorization in Hive, essentially how you control who gets to see and manipulate your data. There are a few key ways Hive handles this. You can grant permissions directly to users, which is pretty straightforward. Alternatively, you can set up session-based access, so someone only has the privileges they need during their login time. And for larger environments, role-based authorization where users belong to roles with predefined permissions is a really effective approach. Hive uses SQL commands like grant and revoke to manage these permissions, allowing you to precisely define what each user or group can do within your data warehouse. Okay, let's talk about how Hive controls who can see and modify your data. There are two main ways it does this. The first is storage-based authorization. Basically, Hive looks at the permissions on the files in HDFS, just like you would with any other file system. So, if a user doesn't have permission to read a particular file, they can't see the data inside that file in a Hive query. It's simple but limited. Now, there's also SQL standard-based authorization, which is Hive's own security model. This means permissions are managed directly within Hive using users and roles. It gives you much more granular control, especially when it comes to things like row-level security, where you can restrict individual users from seeing only a portion of the data in a table. Okay, let's talk about how we can really dig into why Hive queries are taking so long or consuming so many resources. First off, make sure you've enabled query history. That's where all the queries get logged. Next up, Hive Server 2 gives us a ton of metrics, which is super helpful for understanding what's going on under the hood. Then it's about diving into those execution plans with Explain and Explain Analyze to spot potential problems like full table scans. Don't forget to monitor resource usage, CPU, memory, disk I/ONC, how they relate to your queries. And finally, using log statements within your Hive QL can give you even more granular insight into exactly what's happening as the query runs. Okay, let's talk about a really important difference when working with Hive managed versus external tables. Think of it like this: managed tables are handled entirely by Hive. It keeps track of where the data is stored, makes sure everyone has the right permissions, and even handles things like creating and deleting the table for you. External tables, on the other hand, give you more control. The data lives somewhere else, maybe in S3 or another file system, and Hive just knows about it. You're responsible for managing that data's location and lifecycle. Managed tables are great when you want central management and Hive's smart optimization features. External tables are perfect if you need to store data in a specific place or work with diverse storage solutions. Thank you for watching.